So today is the part 2 of our simulation basics, and we're going to talk about the lab distillations and how Pro2 handles all that data and cuts it into what we call pseudo components. They're not real chemical species, but they're petroleum cuts to represent your stream. So you'll hear me say pseudo components. Sometimes I'll call them petro components. They're the same, so they're interchangeable. Then I'm going to go over the column model in Pro2. We're not actually going to run one unless we have time, and maybe I'll have a volunteer come up and run one, but I was just going to show you some that's already been done, and we can look at how it was set up. And we're actually going to have a little exercise in class together to translate an existing column into Pro2. So you would take an actual column out in the plant with real trays, and you're going to have to translate them into equilibrium stages. You need to see how many you need and where does the feed go in, and if you had any side draws, where they would come out. Did anybody have any questions from last week? If you had a chance to run the problems, if you wanted to. Anything? No? Then we'll go on. So what is a petroleum assay stream? You'll hear me say an assay. What it is a breakdown of a petroleum-based stream. So, for example, if you take a crude oil, it contains thousands and thousands of distinct compounds, methane, ethane, and so on and so forth. But it's not feasible to enter all those components into your simulation. You'll be sitting there all day typing it in. Plus, you don't really have the luxury of having that kind of data. You don't have 1,000 component breakdown of your stream. So what you'll have is a set of numbers that will represent your stream. And usually they'll include distillation data, and that'll show you the volume percent versus the temperature, and I'll show you that shortly, and the gravity data, and they will try to capture the light ends or the lighter components of that stream, and try to run it through a gas chromatograph or some sort of analytical instrument to tell you what kind of light ends you have in that stream. So this is something I cobbled together to show you. It's very simplified, of course, but what they would do is they would take, say, your crude oil and just dump it all into a flask. Then they heat it up. And then the vapor, well, this is a thermometer, and it's closed. This is supposed to be a stopper. The vapor will come in here and gets condensed. And the first drop that comes out, they will look at the thermometer and say, okay, that's what I'm going to call the initial boiling point, or IBP. And sometimes the initial boiling point is really not the real initial boiling point of the stream, because depending on how long that sample's been sitting in the lab, some of the light stuff may have escaped. So sometimes they call that a loss if you're doing a D86. This is more representative of the D86. So you would keep boiling, so they would come down, the next drop will come down, and then they would look at the volume and how much has been collected, and look at the temperature and say, okay, that's the temperature at which, say, 5 volume percent's been collected. And then they'll make a curve or a table of the data. So for D86, it looks kind of like this. And now I'll explain what D86 is in the next few slides. And then for a TBP, or a true boiling point curve, they actually have a little distillation column here. It's what they call a fractionation still, with little trays inside, and it's actually refluxed. So that, you can see, is probably going to give you a more accurate representation of your stream, but it's very expensive and very time consuming. So you're probably going to see D86s, D1160s. For D1160, you actually have a little vacuum connection here, because it needs to pull a vacuum, and I'll explain that. So you end up with something like this: the liquid volume distilled, whatever's collected in that graduated cylinder, and the temperature at which it was collected. So you have, a little curve like this, and it will be, if it were in a table, it would look something like this, like 3 volume percent. It was at 97 degrees, 3 volume percent has boiled off, and we collected it, and so on. So you'll see it gets heavier and heavier. And here are the light ends analysis. They've captured the light ends, and they've broken down the composition, usually through a chromatograph. And in this case, the light ends are 3% of the entire stream. So for true boiling point, as I mentioned, you actually use a fractionation still. And because it's very precise, sometimes you'll get big steps. Remember the curve that you saw a few slides back? It was nice and smooth, but if you're doing a true boiling point, you may actually get big steps because you have pure components boiling off. Okay. And you just use this directly to get the normal boiling points for the pseudo components, and I'll explain that in Pro 2. So pseudo components, again, are petrocomponents. Those are the approximations of your stream. And it's very expensive and takes a long time. And they usually report it at 760 millimeters of mercury. And because of the heavy ends, I don't know if you remember when Helmi was explaining before, if you heat up something past maybe 650 degrees Fahrenheit, they'll start to crack. So to avoid that, they will actually run the heavier ends. They'll pull a vacuum and then correct the results to 760. So when you do get results from the lab, you need to be careful to see if they've actually corrected it or not. For example, if your lab's in Denver and it's a mile above the sea level, and they're reporting, say, 100 degrees Fahrenheit, but in order to correct it to 760, they actually need to add like 10 degrees to it because they're at 650 millimeters of mercury pressure instead of 760. So, and when it gets to higher temperatures, like 600 degrees, for example, they actually need to add like 20 degrees to it to correct it to 760. So it could make a big difference. There's another method called the ASTM D86, and basically there is a society, American Society of Testing and Materials. They have very precise procedures for the labs to follow in order to run these tests. And this is fast and inexpensive, and you can reproduce it usually within a few degrees. And as I mentioned, the first drop is recorded as the initial boiling point, so the first drop that's condensed. They'll write down the temperature that they read on the thermometer and say that's the initial boiling point. And the last drop is recorded as the end point. And then you'll have some things left there in the bottom of your flask, and they call it the resid or the residuals. Now, in order for Pro 2 to use the D86 data, they need to convert it to a TBP basis before they can do any math with it to cut it up. Okay. And as I mentioned, the cracking means the long chains of hydrocarbons will break. At high temperatures that will happen. And you can actually use a cracking correction inside Pro 2 to take into account cracking. The D1160 is for heavier streams, and they do need to run it under vacuum because, the cracking, you don't want it to go above 650 degrees or your material will crack. And so normally they'll run like TBP test, and then for the higher boiling mixtures, when they pull a vacuum, they actually can get better separation. So a lot of times you'll run a TBP to like maybe 50%, and then the rest do a D1160 to represent the heavier materials. Now there is a simulated distillation procedure. It's called ASTM D2887, and it actually uses a chromatograph to separate the components, and it usually is reported in weight fractions. and it approximates the TBP pretty well. And so I'll explain later that you want to just go ahead and enter your data as TBP instead of D2887, because Pro2 will do a double conversion. It'll convert D2887 to D86 and then D86 to TBP. So a lot of error will be introduced. So it's probably just, you just put it in as TBP to avoid that double conversion error. Okay. So how does Pro2 take this data and create pseudo components for you? It will look at your curve that you've entered, and then you need to provide it light ends data if you have it, and you usually should, because that's very important. It'll go, is your overhead product. And then you need gravity data. You usually will get an average gravity for the stream. And if you're lucky, or if your lab did any more tests, you may get a gravity curve. And once you have that information, it has correlations in the program to get other properties like molecular weights of each cut, volume flow rate of each cut, for example. Then you'll take these pseudo components and model the streams. Remember last week we talked about how the streams has composition like methane, ethane, and it was very, obvious how much of each is in each stream. But in this case, you're going to get these pseudo components, and they're going to look a little funny, and I'll show you what they look like when it cuts it up. And then when it uses that to run your flow sheet, calculate how much is going to go overhead, how much is going to go to the bottoms. It needs to give you an output, and then during the output, it'll actually print it out in the TBP or TBP, D86, D1160, and D2887 format. So you can see what your endpoints are for each cut, each product. Let me just go to Pro2 and show you so it's a little more clear. I didn't mention this last week to the ones that were here on Wednesday, but I did it yesterday. There's something in Pro2 called application libraries, and those are problems that they've already solved for you, or flow sheets that's already been made for you. So you can use those as a starting point, or just to get an idea of maybe what thermal they used on it. So I just searched for app libs, and they're pretty useful because there's quite an extensive amount in there. App lib. And for example, like right now I'm going to get a crude distillation column, this one. And I could look at the flow sheet. And it has a crude column with 3 size strippers. So then I remember the name, it's called R3R. And these are all in input format, in the keyword ASCII format. So I need to go import them. So I would do File, Import, and I'd find App Libs folder, and go to R3R. Now it's importing. Okay, so this stream here, if you notice, last week we did the composition defined stream. Well, now this one is a petroleum assay. And if you click on this, the flow rate and assay, this one is 5,000 barrels per hour. And here's that data that I showed you before in that slide where you put in how much was distilled and then the temperature at which it was recorded. So you go down, down, down until usually you don't get to 100%, but in this case they put in 100%. And if you have any light ends, you would put it here. And those you need to pick from that benzene ring as we did last week. We have water, ethane, propane, IC4, NC4, and then these add up to 3, and since they're in liquid volume percent, so it's 3 liquid volume percent of the entire stream. And if they don't add up to 1 or this number, then you need to normalize it. Okay, so I wanted to show you what happens I'm going to run it and show you the what the pseudo components actually look like when it's in a stream report. So I'm just going to lay down a stream property table and make it really big so you can see it. See these NBPs? NBP stands for normal boiling point. And so the first component that it made from that data we enter, that curve, would have a normal boiling point of 111 degrees Fahrenheit, and you can see it gets heavier and heavier and heavier and heavier. So this component is like the heaviest in your stream. So this will be used for your entire flow sheet to calculate, what's coming out the side, what's your naphtha, what's your kerosene, what's your diesel and jet fuel. And you'll see that for naphtha, for example, these lighter components it'll be populated with some numbers, and then the middle stuff will be here. You'll see some numbers here, and the rest will be 0, and so on and so on. So your resid will be down here. I didn't show you this, but you'll see for the assay, you also need to give it an average gravity. It could be API, specific gravity, or the Watson-K, and I'll go over the equation for that. Or you can supply it in the curve if you have that data. And this pressure is at, where's millimeters of mercury? Okay, so it's right at 760, so that's good. Okay, any questions so far about what an assay is and what a pseudo component would look like? Yes?
How come they have more normal boiling points compared to the amount of products coming out of the distillation?
Oh, you mean the actual library components? This, by default, I'll show you the cut points. It will make a cut like every 25 degrees from 100 degrees to 800 degrees of your curve. So it just happened to end up with, like, say, 25 components or something. And then it goes on, and then this will end up with like this many sets, depending on the cut points that you define. And I'll explain why that's important. But yeah, you usually would end up with a huge set of pseudo components, depending on your feed, but usually you'll get something like this, pretty much. And then your light ends are usually just defined by anything that's C5 and up. Anything C6 and below, you would, group it into your assay. So let's go back to the slideshow. Oh, sorry, one more thing. I wanted to show you how it would translate your product streams. Like, for example, actually, let me just put the products here. So even though it'll be really hard to read, we can at least see how they're distributed amongst those pseudo components. Okay, I'm going to make it smaller. Maybe just a few streams, I guess. I don't even know if you could read that. It's really hard to read, sorry, but let's see. The top crude, and this is the size. Let me just get the stream. Oh, I didn't show you these last week either, but these are the search. Like, if you click on this and you click on a unit op, it will center it. But right now they're really small. Let me just go ahead and just make this bigger. Escape. Right. even bigger. Okay, so let's see. This stream is liquid. See results. So this stream here, oh, that's just water. Sorry, picked the wrong stream. This one. View results. Okay. So you can see that's a pretty light stream because it's coming from the overhead of your column. So these, the first 1, 2, 3, 4, 5, 20 odd components have flow rates in them. See that? So the rest are like almost zero. And if I had asked for more than one, asked for the other streams, you'll see the middle ones will have numbers here and zeros up here and zeros down here until you see the heaviest things will have numbers here and zeros everywhere else. Okay. And what was I going to show you? Okay, so let's go back here. Oh, the assay's translating back. So if I were to look at the output, let me just generate it. Scroll it all the way down. You will see a set of numbers that look like this. So your feed, it will generate a TBP curve for you at different pressures. And D86 at different pressures, then D1160, then D2887. So this is important when, say, you want to make a endpoint spec on, say, your naphtha. And so you would look at the 95% point to see if it's close to the number that you want it to be. This is pretty heavy stuff. So that's what I meant by Pro2 will translate it back to a distillation or an assay for you to look at. Okay, so next. So I showed you how you would select petroleum assay instead of component define, right? And then you just enter your data, like the volume percent and the temperature. Then you must provide the flow rate and the gravity data. You could put in the API gravity, and you all did the homework on that, so you know what that is. The higher the gravity, API gravity number, the lighter the component is, or the stream, I should say, or specific gravity, or you could put in what they call a Watson K factor. Sometimes it's called a UOP K factor. It's like from Professor Watson of University of Wisconsin, or Universal Oil Products. The K is a measure of the paraffinicity. So it's a paraffin is like a wax, right? And it's usually like a straight chain hydrocarbon. So the more straight chains you have in your stream, it's the more waxier or slipperier it is. And so if you see a Watson K of like greater than 13, then you know you have lots of paraffins in that stream. And if you have a lot of rings like benzene, toluene, xylenes, you'll see a Watson K factor of less than 10. And here's the equation for Watson K, and that's why if you were to provide Watson K, it could figure out specific gravity from there, or even API gravity. So this is the equation. It's like the cube root of the normal boiling point over the specific gravity is 60 degrees. Now, if you have a weathered sample, it means all the light ends have escaped. Sometimes they would have provide you with a separate light ends data, and you may have to mix it with your assay stream to get your combined feed. Or sometimes they would report that light ends with your assay. Like the one we just saw, it was 3% of your entire assay, so we put it in with the assay, in the assay data section. Okay, so if it's not provided as part of your assay, you need to mix it and make a combined feed and then feed it to your column or whatever unit operations you're using. Now, if you have molecular weight data from the lab, it's usually pretty rare though. It's best to provide it because the correlations in the program are the least accurate of all those used in the characterization of your pseudocomponents. So if you also have sulfur content, pour point, anything that the lab gives you, you may want to enter it so it's more accurately predicted for your output. So how does Pro2 take that assay data you give it and cut it into a set of pseudocomponents? And so this is what it does, as a very high level overview of it, and then I'll go into each one in a little more detail, but not in too much detail. Basically, whatever you give it, like a D86 or a D1160, it'll need to convert it to a TBP at 760 millimeters of mercury. Then it'll cut it up, and when I say cut, a cut is just one pseudocomponent. So it'll actually go through a smoothing routine here to make the curve smooth, and then cut it up into cuts. Then for each cut, it'll decide how many moles are in that cut, and how much, how many kilograms per hour or whatever, and how much in terms of volume. So it does a quantitative analysis here. Then if you have light ends, it will process them, add it to the curve. Then with all that, it'll determine the average normal boiling point, specific gravity, and molecular weights for each component. Then from these three properties, it could characterize other thermal-physical properties. Then after all that, it gets finished calculating, you get your set of pseudocomponents. Okay. And as I mentioned a little bit earlier, that it does have to smooth the curve for you, and it has three methods to smooth that. And this is all math, right? It's all curve fitting methods. And the first one is cubic spline. That's the default. And if you don't have like an initial boiling point and an end point, say you only have like a 5% point and a 95% point, it will use something called a normal probability function to extrapolate the data. It'll take the last, I think the first 2 points you provided, then it will just extend it down to 0 for the initial boiling point, and same for the heavy ends, it will extend it up to 100. So if you do have steps, you may come across some fitting problems. Let's see, and then there's the quadratic polynomials. Like, again, this is all math. If you want to look it up for the details, it does have it in the help. And then the probability density function uses a least square fit. That's, it tries to minimize the distance around the root. So it says recommended when errors are suspected in the data. If you're like plotting your data, I don't know if you need to plot it, but if we used to, and if you see it like a big jump or something, usually the lab reported it wrong, or they may have transposed some numbers, and if you use this, it will help you get around those errors. Or you can manually remove those points. Okay. So the first 2 data points, as I mentioned, gets to be used to extrapolate back to, it's not really 0% because, it's not a perfect world. Things escape, and then you can't boil everything off. So it's arbitrarily set to be 0.01%, and then the endpoint is 99.99. So here are the cut points I was explaining to you about how many components you'll end up with. By default, Pro2 will take between 100 degrees and 800 degrees Fahrenheit. It'll make a cut every 25 degrees. So you'll get 28 components in this range. And then from 800 to 1200, it'll make 50 degree cuts, and you'll end up with 8 components. And then the heaviest part, every 100 degrees, and you'll get 4 components. And let me show you that graphically so it makes sense. Go back here. Here's my feed. So if you look at the curve here, good, all right, that looks pretty good. This is a temperature axis, and this is a percent distilled. Now, if you look at from 0 to 800, let's say around there, what it does is it'll go up, and every 25 degrees, it'll come over here and make one cut. This bar here, that's one cut, or one component. Here's another. So every 25 degrees makes a cut, every 25 degrees, until it gets to 800, and then it's every 50 degrees makes a cut. So 50 degrees makes a cut, 50 degrees, until it gets